Aloha, my name is Robert from Ne'epapa Kahana, and welcome to the Online Professional Development for Module 13 of the Canoe project. To begin, let's go onto our website, www.stemd2.com, and after we've logged in, let's go ahead and go on to Students, and let's build a canoe. Module 13 is in Unit 5 of the Go Math book. Let's go ahead and go down to Module 13. Here are the list of activities for Module 13, which is about volume. The first activity that we'll be talking about will be Canoe 13.2.1. In this activity, we will be learning about fishing throw nets. A throw net is typically circular in shape, with weights along its perimeter. When the fisherman throws the net, the weights pull the net down. The weights often cause the net to form a cone shape as it falls. In this activity, we will use the formula for the volume of a cone in order to figure out how much water is inside this net. So here we have a net with light weights. Here's a net with medium weights. And here's a net with very heavy weights. They have slightly different shapes due to the different weights, and this might mean that they have different volumes. After you've figured out the volumes of the three nets, please take some time to compare them. In the next activity, we talk about the fishermen, Kumuahi and Kumuaku. Kumuahi and Kumuaku are fishing in two different ponds. The pond that Kumuahi is fishing in has 5 fish for every 100 cubic feet. Kumuaku, on the other hand, is fishing in a different pond that has 9 fish for every 100 cubic feet. The shapes of their ponds are different, so they use different throw nets. Now that we have the volume of the nets measured in cubic feet, and we also have the concentration of fish measured in fish per cubic feet, we should be able to calculate how much fish did Kumuahi and Kumuaku catch with each throw. We asked the students to figure this out in question 3. Finally, we conclude this activity with an open-ended problem. As you can see here, the shape of the nets change with the different weights that we attach to it. Now we want to think about what happens when we put super heavy weights and super light weights onto the net. As we mentioned, this is an open-ended problem, and we don't want the students to worry too much about being right or wrong. We just want them to come up with a logical answer and be able to articulate their answer with their classmates. Considering extreme conditions, such as a net with super light weights or a net with super heavy weights, is a technique that we often use in math and science. Whenever we find a new understanding of nature or mathematics, what we often do is we consider the extreme conditions, and then we ask ourselves, does our understanding still hold? More often than not, we find that the misunderstandings that we have about the world, which we take for granted, become super obvious when we consider the extreme cases. And we, as lifelong students, can learn a ton from these experiences. That's it for this activity. Please pause the video and take some time to review and reflect on it. Aloha, welcome back. The next activity that we'll be talking about is Canoe 13.3.1. Here's a picture of an ipu, which is the Hawaiian gourd. It is often used as a percussion instrument in hula. Because it's big, strong, and light, we often use it for carrying water and food. In this activity, we want to help out Canoe and 4 of his friends who are planning a 30-long journey to sail from Tahiti to Hawaii. The 5 of them need to bring 2 liters of fresh water per person per day. In this activity, we first ask the students to figure out how much water do they need for this journey. Luckily, Canoe found some large ipu that have an inside radius of 12.5 centimeters. With this information, we can figure out how much water one large ipu holds. We can also figure out how much large ipu does Canoe and his friends need in order to have enough water for the trip. Canoe also found some medium-sized ipu with a radius of 10 centimeters. If Canoe wants to use the medium ipu instead, how many does he need for the trip? In the next question, we see that Canoe uses a combination of medium and large ipu for the trip. If he has 3 times as much medium ipu than he does large ipu, then we can form a system of linear equations and we can figure out how much medium and how much large ipu he brings for the trip. Now we have a menehune, which is a mythical being in Hawaiian mythology. The menehune came by and offered an ipu that's big enough to carry everyone's water. In this question, we ask for the diameter of this ipu. So in this question, we start off with the volume and we work backwards to get the diameter. That's it for this activity. Please go ahead and pause the video and take some time to review and reflect on it. Welcome back. Let's go on to our last activity, Canoe 13.C.1. In this activity, we're going to learn about something called density. Density helps us to figure out whether something will float or sink. To measure density, we first need a mass, and then we need to calculate the volume. And then density is mass divided by volume. So here, for example, we have a block of ice that has a mass of 29.9 grams. It also has a volume of 32 centimeters cubed. This gives us a density of 0.934 grams per centimeter cubed. This is important because it turns out that if you put something in a fluid, if it is more dense than the fluid, it will sink, but if it is less dense than the fluid, then it will float. Liquid water is a fluid that has a density of 1 gram per centimeters cubed. Since ice is less dense than liquid water, we can see that ice floats on water. In this activity, we will calculate the densities of 3 other objects, and then we will determine whether or not they will float in water. So the first object is this cylinder that has this mass, this radius, and this height. And then we have a cone and a sphere. So first we need to calculate the volume of these 3 shapes, and then we use the masses to figure out the densities. And then we can figure out whether they float or sink. The next question helps us to check whether we understand the connection between density and floating. So let's think about a floating metal battleship and compare it to a floating wooden canoe. Are the densities of these objects greater than or less than water? This may be counterintuitive to some, but they're actually both less dense than water because they float. Next, we have 2 open-ended questions. The first one asks the students to name several other things that are less dense than water. In the final question, we are reminded that objects that are more dense than water will sink, and objects that are less dense than water will float. But what happens when you have something that has the same density as water? We ask the students to think about this on their own and come up with a hypothesis and articulate their logic to the rest of the classroom. That's it for this activity. Please pause the video and let us know what you think. Hello, thanks again for joining me for Module 13. We'll see you again for Module 14.